Today we're going to be taking a look at solutions and concentrations. First, some terminology though. A solution, homogeneous mixture of two or more substances in a single phase. The solute is the substance being dissolved, and the solvent is what is doing the dissolving. In other words, a solute is dissolved into a solvent in order to create a solution. Now we tend to think of solutions as something solid dissolved into something liquid, like salt or sugar dissolved into water. And while that is very common, there's lots of different possibilities. Any phase can be dissolved into any other phase and create a solution, as long as it's a homogeneous mixture, so the mixture looks the same all the way throughout. Here's a couple different examples of things where your solute is not necessarily solid, and your solvent is not necessarily liquid. What you looked at in your sugar cube lab were different factors that affected the rate of dissolving, how fast you can get that solute to dissolve. Hopefully the things that you figured out were that the surface area makes a difference. The smaller your pieces, the more total surface area your solute has. Stirring certainly has a big impact in how fast something dissolves. And the temperature. The higher the temperature, the more kinetic energy, therefore the particles move faster and can dissolve more quickly. What all three of those factors have in common was that they allowed the solvent particles and the solute particles to get in contact with each other faster. And the more contact they can have and pull into solution, the faster something's going to dissolve. The next thing we're going to look at, though, is not just the rate, but the solubility. Solubility is the amount of solute that can dissolve, not necessarily how fast it dissolves. So some factors that would affect the solubility first would be the nature of the solute and solvent. The phrase that textbooks tend to use are like dissolves like. In other words, a solvent will dissolve a similar solute in terms of intermolecular forces. So a nonpolar solvent can dissolve a solute that is also nonpolar. A polar solvent can dissolve a solute that is also polar. And ionic compounds are going to fit into this category too, because ionic is basically so polar, the electrons aren't shared at all. So polar will dissolve polar and ionic. So with that in mind, take a moment, pause the podcast, see if you can figure out which of these will dissolve in water. Water is polar, therefore anything that is polar or ionic will dissolve in water. Sodium hydroxide is ionic, and then these last two are polar molecules, so they will all dissolve in water too. CH4 is nonpolar and therefore would not dissolve in water. Next factor we'd look at is temperature. We already mentioned temperature as something that would increase the rate of dissolving, but it also tends to increase the solubility itself. The carrying capacity of that solvent is higher because of that greater kinetic energy you get with higher temperature. So temperature is the only one of these factors that affects both the rate and the amount at the same time. With gases, however, as your solute, the relationship's not quite the same. In this previous graph here, you can see the blue lines are showing you positive slopes. These are all solid solutes, and for the most part, the greater that temperature, the higher the solubility. However, for gases, these are all gas solutes trying to dissolve them into a liquid. The higher the temperature, the less solubility they tend to have. So temperature can do a couple different things. This does bring us to some more terminology, though, comparing solute to that carrying capacity. An unsaturated solution would mean it's got less solute dissolved currently than the solution can hold at maximum. A saturated solution is the maximum amount of solute is dissolved, so it's exactly at its carrying capacity. And a supersaturated solution means you've got more solute dissolved than the solution can possibly hold. Now this is a tricky situation to do. You can't just take a saturated solution and throw more solute into it. The solute won't dissolve. However, what you can do is heat up a solution, which increases the carrying capacity, dissolve more solute, and then very slowly cool it back down. You don't always have the extra solute coming out of the solution immediately, so you can temporarily keep more in there than it should be able to hold at that temperature. It's very unstable though, so if you do anything to bother that solution, the excess should precipitate out or come out of the solution. So now I can go back to that same graph that you saw a couple of slides ago and look at them a little bit more closely. What these solubility curve graphs tell you is what the saturation point is, depending on the solute and the temperature. So while they're called solubility curves, you could also call them saturation curves. They are telling you, based on the temperature, how many grams of the solute can be dissolved for every 100 grams of water. So a lot of the questions you'll see for solubility curves really are just graph interpretation. Can you take a look at the information, compare it to the graph, and see what you're looking at? If you can plot a point that's below the curve for that solute, it would be an unsaturated solution. If you plot a point and it lands right on a curve, that would be saturated solution. If you plot a point and it's above the curve, that means you have that unstable, temporary, supersaturated solution. So take a moment, pause the podcast, see if you can figure out the questions there for your turn number 2. First one says, if I have 100 grams of KBr dissolved in 100 grams of water at 60 degrees Celsius, what kind of solution do I have? So this graph is telling us per 100 grams of water, as it's written. So that just means I have to go to 60 degrees, 100 grams of solute. That would give me a point right here. The line for KBr is right there. If I'm above that line, that would mean I've got a supersaturated solution. The next question, though, gives you the same circumstance, 100 grams of KBr, 60 degrees Celsius. However, I have twice as much water. Twice as much water would mean twice as much capacity for holding the KBr. So according to this graph, the line crosses 60 degrees at about 85 grams or so. But if I double the amount of water, I double that capacity. So I should be able to hold about 170 grams of KBr in 200 grams of water, which means that 100 grams that I have would be an unsaturated solution. Now, a term that we saw in relation to double replacement reactions is precipitate, and it still means a solid coming out of aqueous solutions. So with that terminology then, take a look at that your turn number 3, see if you can figure out how to interpret your graph. All right, I've got 260 grams of sugar dissolved in 100 grams of water, which means I can read the curve as is, at 60 degrees Celsius. So that would put me right here. That is unsaturated at that moment, so I should be able to dissolve that much sugar. But then I drop the temperature down to 0, so that would put me right here. How much sugar should precipitate out of the solution? Well, when I drop the temperature down, this is now the amount of sugar I have that is over the capacity at that lower temperature. So the difference between 260 and 180 is the amount of sugar that should come out of the solution once I bother that a little bit. And 80 grams then is the amount that should precipitate out, because that's how far over the capacity I am at that lower temperature. Next thing we'll take a look at is how to describe this amount of solute in a solvent quantitatively. So we're going to look at units we can use to describe concentration. The most common unit you're going to see is molarity, which is defined as moles of solute over liters of solution. So it's moles as compared to a volume. There is another unit that's a little less common, but will have one important application later on, and that is molality, which is similar. It is also moles of solute, but we're dividing it by the mass of the solvent in kilograms. So molarity is moles per volume in liters. Molality is moles per mass in kilograms. Make sure, by the way, when you're writing these things out by hand, make sure you can tell the difference between your upper and your lowercase m's, otherwise that gets confusing really fast. So here's an example problem of how we would calculate these concentrations. If I want to find both units of concentration, given some information here, I've got my solute, my solvent, and the volume of the solution, all the information I need for both units. For both units, I need to have my solute in moles. So the first thing I would have to do, no matter what type of unit I'm solving for, is to get from grams to moles. Then, to calculate the molarity, I have to take my moles and divide by the volume in liters. I was given a volume in milliliters, so you have to move your decimal point before you can plug that in. To calculate molality, I need a mass in kilograms. So I had a mass of my solvent in grams. Move your decimal back to change from grams to kilograms before you plug that in. Here's one for you to try. Just like the previous example I showed you, pause the podcast, see if you can work through this. First thing you got to do is take your solute and change it from grams to moles. So one-step mole conversion should be very comfortable at this point. To find the molarity, you have to divide moles per liter. So take your volume, and because it was in milliliters, you had to convert to liters before you could plug it in. To find molality, you have to divide your moles by the mass of the solution in kilograms. So here's my solvent, the water. I take that mass in grams, and because I started in grams, I do have to move my decimal point to change from grams to kilograms. Okay. Last thing we'll talk about is looking at how some things can break apart into ions as they dissolve, looking at this dissolving process. A useful property for characterizing solutions is their conductivity. And that level of conductivity depends on how many ions are present in the solution. We can have strong, weak, or non-electrolytes based on things that are either made of ions, like ionic compounds, completely break apart, or weak acids and bases. Some of them will come apart into ions and some won't, so you get a weak electrolyte. Or non-electrolytes would be things that are covalent compounds. They don't break apart into ions at all. They're just polar and therefore dissolve in water. Here's a picture of what this would look like, the way you would test for something as an electrolyte or non-electrolyte. So we can see here on my picture, no light in this light bulb because I have a polar covalent substance. A non-electrolyte does not break apart into ions at all, as opposed to my ionic compound is a strong electrolyte because you can see that the entire thing splits into ions as it dissolves. A weak electrolyte is going to be either a weak acid or a weak base, and you can see some of the molecules break apart into ions, whereas most of them do not. Now, the idea of a strong electrolyte is going to be important for some things we do later. So we want to see how exactly that breaking apart process looks. So dissociation is that process of an ionic compound breaking apart into its individual ions. So if I take an ionic compound like calcium nitrate, for example, and show what happens when it dissolves, all of these individual ions are going to separate from each other. So I've got my calcium ion, and I have two individual nitrate ions that all come apart. Then if I were to ask how many moles of ions I get from 1 mole of calcium nitrate, just look at your coefficients. Every 1 mole of this ionic compound splits apart into 1 calcium and 2 nitrates. So I have 3 individual pieces total. With this as an example, pause the podcast and see if you can do a couple on your own. For that aluminum chloride, breaks apart into 1 aluminum and 3 chlorines. So since they're not connected to each other anymore, I've got my 1 aluminum and my 3 chlorines. 4 pieces total, 1 aluminum, 3 chlorines. For the next one, you have to be careful when you've got a polyatomic ion. Make sure that polyatomic ion stays together as one group. So that potassium dichromate, you will get 2 separate potassiums, because they come apart from each other. And then you have 1 dichromate, 1 polyatomic ion that does stay as a chunk, which means you have 3 moles of ions total when this potassium dichromate dissolves. 2 of them being potassium, 1 of them being dichromate. Very last thing, so if we can put all this together, our concentrations and our dissociation equation. So if I have 2.8 moles of potassium dichromate dissolved in 3.6 liters of solution, here is that same dissociation equation we looked at just a moment ago. See if you can calculate the molarity of the solution and the molarity of each ion. Pause the podcast, give it a shot. The molarity of the solution should be pretty easy. Moles per liter, and you were already given them in the correct units, so just divide moles per liter. Now the molarity of each ion is going to require you to look at these ratios. So this is a one-step stoichiometry problem. Can you look at the mole ratios you've got here? To calculate the potassium, I know I've got this 0.78 moles of potassium dichromate. That's what we just solved for, so that's my starting point. These are the coefficients from our dissociation equation. I have 2 moles of potassium for every 1 mole of potassium dichromate. So set it up as a one-step mole ratio problem. 1.56 molar potassium is going to be what you get. Same deal for the dichromate. I have my 0.78 molar dichromate, 1 mole of dichromate for every 1 mole of potassium dichromate, because they both had coefficients of 1s. And there you go. That is the end of the line.